Okay, well, I'll make a start then. Well, morning everyone. So my name is Mark Wilson. A bit of background from myself. I'm an academic in mechanical engineering. I originally started out studying maths and physics and did a PhD in applied maths here in Leeds in the area of fluid dynamics, and then moved over to mechanical engineering, where I've been ever since. I've been in Leeds for a very long time. So for my session today, I'm going to talk about droplet dynamics on surfaces, and I'm going to do this by looking at two recent CDT PhD projects. So one is by Khalid Al-Ghathi, who finished just this year, and the other is Tom Sykes, who finished last year. Okay, so I'm going to be looking at these two projects, and I'll be providing some background information as we go along. Okay, so let's start with the first one then. Well, it's actually the second project to be finished, but the first one I'm going to talk about today, which Oliver was also involved in supervising as well. So this is about impact of liquid droplets onto things like scratches. Okay, so it's sponsored by DuPont Teijin Films, who are a manufacturer of polymer films for various applications. And the project really was motivated by inkjet printed electronics. So printed electronics in general are excuse me, a low cost way of producing high volumes of electronics like displays, so you've got a large area to cover, traditionally they use ordinary traditional printing methods like screen printing and gravure printing, and they can be very fast. But there is a move towards inkjet printing for these applications because there's greater flexibility. You don't have to manufacture masks or screens or anything like that. You can just essentially upload your description of what you want to print and then go away and print it. There's less waste because you're not having to screen off certain areas and mask areas. So you only print what you actually need. And it's a non-contact process as well. So there's a greater range of substrates potentially that you could print onto. Now, as desire for higher resolution increases, droplet sizes decrease. So, for example, we might be down to 20 microns as a droplet size. As the droplets get smaller, then imperfections in the substrate that you're printing on could potentially become more significant. So these could be minor variations from production processes, or they could be scratches during handling. Or it could be things like contaminants, debris, dust, that kind of thing. So what DuPont Teijin Films were interested in was, what effect do these surface imperfections have on printing continuous tracks? So obviously in electronics you need continuous circuits. So is the scope for these to be interrupted by defects like this? So can simulations help with understanding these effects? So that's the driver. Just to help set the working context, I need to make sure you're aware of some dimensionless numbers, and I guess you've already covered some of these. I would certainly expect that you're already familiar with the Reynolds number. So in this context, the Reynolds number is defined in terms of the droplet impact velocity and its in-flight diameter, so that's before it hits the substrate, and the kinematic viscosity, and that measures inertial versus viscous forces. Another key parameter in the context of these surface tension dominated flows is the Weber number. So we have the density, the liquid density coming here, and the surface tension here. So this is really a ratio of inertial and surface tension forces, and you'll often see the word capillary used to refer to surface tension forces. So this is a survey of some previous work relevant to this, which Khaled produced for a paper which he published earlier this year, and also for his thesis. So this is how a lot of people present work on droplets, and you can see there's a lot of work on droplets. So we have the Weber number here along the bottom axis and the Reynolds number, and there's a line here which indicates this is a theoretical line which shows where droplets would splash. So if you're above this line, you'd expect a droplet to splash when it hits the surface, and below that line the droplet doesn't splash. So the inkjet printing regime is in this area where there's no splashing going on, because obviously you don't want things splashing all over the place when you're printing something. You want it to be well controlled. However, there is some interesting work on small scale droplets which actually defy this this splashing threshold and don't actually splash, but I'm not going to talk about those today. So what we're interested in is what's going on in this sort of box here, and you know, there is some previous work, but this is mainly work on substrates which have no features, so just uniform flat surfaces. And the other plot here shows a droplet diameter versus a feature size. So this is where the substrate has some kind of feature, whether it's a groove or a scratch or a deliberate sort of feature. And you can see that most of the work is on millimeter size droplets with millimeter size features, and some work on millimeter size droplets with micro size features. So we're interested in droplets of the orders of microns, 20 microns or so, and similar sized features. So we're interested in what's going on in this sort of box here, and there's only really one previous study that's in that regime. These work up here is actually, it's not on droplet impact, although it deals with droplets. It's on condensed droplets. So the droplets are very small, but it's formed by condensation rather than impact. So that's to give some context to where we're operating in terms of the regimes. And I should have pointed out that the current work is the stars here, the filled red and blue stars, and this is where it's kind of valid in this region. Okay, so I need to talk about a few background concepts. I'll take this opportunity to talk a little bit about wetting. Again, I'm not sure what's already been covered in your course about this, but I'll assume that there's not so much. So wetting is the process by which we replace typically a gas on a solid surface by a liquid. So it's how a liquid spreads over a solid. And we can make a distinction between forced and natural wetting. So if we imagine a droplet that's spreading on the surface, I would call that natural wetting. So that's the situation we've got here in this picture, where we've got the liquid and it's spreading along the surface. So the droplet might have just impacted and it's spreading along. And a key feature is this three-phase contact line where the liquid, the gas and the solid meet. We could also see a situation where we're actually driving a solid into a liquid. So this would typically be a coating process where we're actually deliberately trying to coat the solid with a liquid. That's usually more of a continuous process. And there's a well-known problem called the moving contact line problem, which I'll talk about, which is related to this point, this three-phase contact line here, and the fact that it's on a moving surface, i.e. this interface is moving relative to the solid surface. And wetting is influenced by many factors. It's a multi-scale problem. And just to illustrate that, I've got a few slides here. So let's start with just a droplet sitting stationary on a surface. So we've got two different surfaces here. This is a water droplet sitting on two different surfaces. And you can see that it makes a pretty well-defined angle, which is known as the contact angle, or the static contact angle, with the surface. So we measure that through the water. And so sitting on steel, you can see we've got a contact angle which is a bit bigger than 90 degrees. Whereas on this ceramic surface, I can't remember exactly which ceramic it is, the contact angle is much lower, so the droplet likes to spread more over the ceramic than it does over the steel. So this is a material property. It's a property of both the solid and the liquid. So different liquids on the same surfaces would have different contact angles. So that's really a molecular scale influence. There's also influences on larger scales, and these are some nice experiments that were done not far away in Bradford by Haj Bencrera and his group some time ago now. This is a tank in which there is a tape going through the middle. So it's sealed at the bottom, and the tape plunges through the tank. And the nice feature of these experiments is that the surface of this tape has different roughness on each side. So we've got a smooth side on the left and a rough side on the right. And what these streaks that you can see here are air bubbles which have been generated. As the speed of the tape increases, you reach a point where the wetting becomes unstable and you start to get air entrained. You get these bubbles formed, and so they start whizzing around in this side of the tank, whereas there's not so many on the left. It's still quite clear. So the roughness influences the wetting and the sort of maximum speed at which stable wetting can occur. So this is a microscale influence, so the roughness is on the order of this scale. And then some other experiments which are on a larger scale. These are performed by Kodak, and this is a process where we have a curtain of liquids coming out of a slot here. This is a sheet of liquid which is falling onto a moving substrate. It's moving from left to right. So again, it's a coating process, and we've got a three-phase contact line right at the bottom. What they found was that for different flow rates of fluid coming down the curtain, they could increase the speed of coating, so the speed of this moving substrate. And they looked at when does that become unstable and you start to get air entrained, where the wetting becomes unstable. And they found that the speed was actually dependent on the flow rate. And the key feature of this this system, when we look at the effect of the flow rate, is that it really influences the shape of the domain. So if you've got a high flow rate and a low speed, then you end up with this big region upstream of the contact point, which we call the heel. And as the flow rate reduces, you end up with a smaller shape. So the contact line here sits upstream of the impact point, and here it sits pretty much underneath the impact point. Whereas down here, at higher speeds, it's pulled downstream. So they found that they were able to operate at faster speeds at particular flow rates. So this is an influence on the wetting of the order of centimeters, which is the size of these geometries. So a lot of simultaneous interacting influences on wetting. And there's a nice little illustration here from a group in France where they dropped two spheres. So the spheres are identical, except that the one on the right has got a nanoscale roughness compared to the one on the left. And as they drop into the bath of fluid, you can see the smooth one just plops in nicely and creates very little splash, whereas the rough one generates this huge splash. And that's because the contact line can't move quickly enough over the surface to close up behind the object, and so it leaves this big open pocket. So lots of different length scales involved. So let's say a little bit more about the moving contact line problem then. This is a bit easier to comprehend if we look at the situation where we've got a moving substrate going into a bath of liquid. But we could equally think of this as being a stationary solid and a droplet that's spreading over the solid. But if we look at it this way round for now, if we've got a contact angle of 180 degrees, we don't really have a problem here, because in continuum-based modelling, we tend to have a sharp interface between the liquid here, which is green, and the air, which is up here in white. So all of these lines here are sharp interfaces, and we have different boundary conditions on these. So on the interface here, we have a kinematic condition here where the normal velocity is 0, and here we have a no slip condition on the solid surface. So if this interface meets the solid at 180 degrees, we don't have a problem, because these two conditions are compatible with each other. But the problem arises when we have a contact angle which is not 180 degrees. So we've got a finite contact angle here, which is usually the case. We have a problem then, because we can't satisfy both this kinematic condition of a 0 normal velocity and this no slip condition at this point, because we don't really know which boundary that point should lie on. It's on the moving solid, but it's also on the interface, and we don't have a well-defined normal at this point. So we have a problem at that point, and this results in a stress singularity. Essentially, you can think that the fluid is having to accelerate infinitely quickly from this point in order to maintain this stationary interface while in contact with a moving solid boundary. So this is a problem for continuum-based modelling. So what we tend to have to do in this situation is to allow the liquid to slip over this solid in this region here. And then there's a question of how we do that. We could use the Navier slip condition, for example, or other ideas. And another key problem is that in this kind of modelling, we have to prescribe this dynamic contact angle as a boundary condition on this interface. So the dynamic contact angle is what happens when you have a moving boundary. So typically, as you start to move a boundary, your contact angle will increase from the static value up to some dynamic value. And we have to prescribe that as a boundary condition. And that's a problem because dynamic contact angles are complicated, as these results illustrate here. So these are some experiments of a droplet impacting on a surface and spreading out. And the graph on the right shows the measured contact angle in this line here. So that's measuring the contact angle at these different stages, and you can see that they are, the non-trivial functions of time as the droplet spreads. So it starts off at close to 180 degrees at this situation, and then comes down. Okay, so that's in an axisymmetric case. So if we have a 3D situation, like a droplet on a substrate with a scratch on it, that's going to be even more difficult to deal with. Another challenge is that even static contact angles are not well defined either, because of the phenomenon of contact angle hysteresis. So the static contact angle, so imagine we've got a droplet that's stationary on a surface, like I showed earlier on. I mentioned a static contact angle. That is not actually unique. It depends on what the droplet has done before you measured it. So here's a sort of a conceptual scenario here. If you imagine that we've got a substrate here where we're injecting some liquid through a hole, and it's spreading out at these different stages, 1, 2, 3, 4, 5, and then we stop injecting and we measure the angle. What we'll see is that as we start to inject the liquid out onto the substrate, the droplet will grow until the contact angle reaches a certain value, and then it will start to spread over the surface. So if we stop at 0.5, we can then measure the angle, and that will give us the advancing static contact angle. If we then start to extract liquid, so we reverse the flow, instead of just reversing this behavior here, what happens is the contact angle stays where it is, and the angle will reduce until it falls to a receding contact angle value, and then the droplet will start to, the contact line will start to recede. So if we were to stop again at this point, we could measure another angle, and that will give us the receding static contact angle. So actually, when we talk about a static contact angle, it can have any value in between theta A and theta R, the advancing and receding contact angles. And so that's something that needs to be addressed as well. And that's quite important for printing, as we'll see in a minute. So hysteresis is responsible for how rain droplets can sit on window panes, vertical window panes. Okay, so that is important for printing, because especially if we're printing a continuous track, what we're wanting to do is to print a sequence of droplets and build up a continuous line. Now, if there was no hysteresis, what would happen is that all of the droplets would end up in a big blob, a big sort of circular blob. Whereas what happens in practice is that if we print one droplet, like this one here on the left, and then print a subsequent droplet a little distance away from it, rather than just coalescing into a circle, they will maintain this elongated shape, and that's because we've got an advancing contact angle in the middle here in this neck region, and a receding contact angle here where the droplet has impacted, spread out, and then it's starting to recoil. And so what we see in experiments, these are views from below, we can see that we end up with this elongated shape. So that's important for printing. We do need that hysteresis, and often in the fluids which are used for printing, the receding contact angle is very small, like 0 or 1 degree or something like that. This is also another interesting feature as well, which is known as the drawback feature. So this is related to a kind of a settling time, if you like, an adhesion time. So the droplet on the left has been pre-deposited, and then there's a little gap in time before the second one comes down. And if you look carefully at the left-hand line, you'll see that as the second droplet lands and it spreads into the first droplet, it doesn't actually displace the first droplet. What happens is that the second droplet gets pulled into the first droplet. So that's called the drawback phenomenon. So that's something else which is a bit tricky to capture in models as well. So those are all pretty challenging for traditional sort of computational fluid dynamics models based on sharp interfaces and Navier-Stokes equations. So the method that Khalid used in his PhD was a different method known as the Lattice Boltzmann method. And I'm not going to go into too much detail on this, but I just wanted to point out the sort of key differences between this and more traditional CFD type approach. So instead of starting with a Navier-Stokes equation and discretizing them into a large matrix system that you can solve for the velocities and pressures, this has origins in kinetic theory and statistical mechanics. So it comes from the Boltzmann equation, which is a transport equation for this particle probability distribution function f. So you can think of this as being the probability of finding a particle close to position x with a speed that's a molecular speed close to xi at some specific time. And if you integrate this over the range of molecular velocities, then you'll end up with the density of particles at that particular point. And if you then take the first moment of that with the molecular velocity, so you integrate this, you'll end up with the momentum. So these are macroscopic quantities on the left, and these are the sort of microscopic probability functions that you have in the integrals here. So the dynamics is all in terms of these probability distribution functions, but they are related to the macroscopic behavior through these moments. And then by doing these integrals by quadrature, we introduce some discrete molecular velocities. So there's some specific molecular velocities, and that introduces the idea of this lattice, where you think of information as jumping from one site to the next, so one node to the next in the lattice. You can see that we've got here 9 different velocities in this diagram. We've got a velocity where the particle stays where it is, so it's 0 velocity, and then it could jump 1 unit in any of these 4 directions in a time step, or it can jump in this along this length. This is a length of √2, a bit longer in each time step. So there's actually 3 different speeds and 9 different molecular velocities there, and that provides us a way of working out these macroscopic quantities from these microscopic ones. So you can think of it as a bottom-up approach. And actually, you can show that the Navier-Stokes equations can be derived from a suitable expansion of this Boltzmann equation. So the way the hydrodynamics emerges from this is we model the dynamics of these distribution functions, and specifically we look at how they relax towards an equilibrium value. The equilibrium is given by a Maxwell-Boltzmann distribution here, which includes the macroscopic velocity here in the expression and the macroscopic density. So on each time step, the particle distribution functions are relaxing to equilibrium, and the equilibrium it evolves as well, because remember that the velocity and the density are calculated from the F's and fed back into these equilibrium distributions. So you can think of the relaxation of the distribution functions as being on a time scale related to molecular collisions, i.e. a time scale related to the fluid viscosity, and then the hydrodynamics emerges as this equilibrium changes over time. In discrete form, it looks like this. So the process is that we start off with a distribution of f, so these are the discrete distribution functions, and at each time step we update those and move them to the next lattice site. So it's a combination of the collision process. There's some forcing terms as well. This is where we can bring in some multiphase effects. So they relax towards the equilibrium, and then we move them to the next site. So that mimics the molecular collision and then the molecular motion from one site to the next along its own particular direction. We then recalculate the density and the velocity, and we update the equilibrium distribution function, and then we go back and repeat it. So it's a very simple algorithm. It's the physics behind it which is more complex, and the algorithm itself is quite straightforward. It's also highly localized because we're only really exchanging information between one node and its nearest neighbors. So there's no large matrix to invert, as in normal CFD, which makes it very good for parallelization. However, there are 19 discrete velocities in 3D. So unlike CFD, where we just have 3 velocities and a pressure, we've got 19 things to keep track of, and then we work out the velocities, and the pressure is related to the density by an equation of state. So it's a rather different kind of approach. We can include multiphase effects through forcing terms. I'm conscious of time, so I'm not going to go into too much detail of those, but we have an equation of state which links the pressure and the density. This is the volume here, so that 1 over the density. So we have two stable phases here, a liquid and a vapor, which allows us to model these multiphase effects. I'm going to skip over this because I'm conscious of time. Now, to deal with contact angle hysteresis, we could actually, I shouldn't skip over that. It's quite important. I'll just go back and talk about how we include wettability. There's different ways of doing this. Essentially, what we need to do is somehow to account for the intermolecular forces which are going on at the solid surface. So how does each phase? So the red phase here is a heavy one, and the blue one is a lighter phase. So we expect under gravity that this red phase here to go downwards. This is between 2 solid boundaries, so it's like a channel with a blob of heavy fluid in it. And so we need some way of accounting for the intermolecular forces at the solid surface, and a simple way is just to use a density which is somewhere between the liquid density and the gas density. So if we set the density on the surface of the solid to be equal to the gas density, then the red fluid won't wet the solid, and it will just have gas next to it. And equally, if we set the density of the solid equal to the liquid, then it will just be covered by liquid and we won't have any gas in contact with it. So if we have a value that's between the two, we should be able to get some kind of contact angle which is between 0 and 180 degrees. And this illustration shows that if we have a small contact angle, then the red fluid likes to wet the solid, and so when it drains down this channel, it leaves behind these big films behind. Whereas if we have a high contact angle, the red fluid doesn't like to wet the solid, and so it quickly de-wets and actually loses contact with the solid. So that's one way of doing it. Another way is to use a more geometric argument where you actually relate the gradient in the density. Because one thing I forgot to mention is that in this method, the interface, rather than being a sharp interface, is a diffuse interface. So it still changes quite rapidly from one phase to the other. You can see the white bit here is the interface. So you can see that it's not a sharp interface. It changes quite rapidly but smoothly between the two phases. And so you can use the gradient in the density to define a normal direction and then work out what does the density on the solid need to be to give you a certain contact angle. So to capture contact angle hysteresis, we could adopt one of two approaches. We could either try to capture the cause of hysteresis, which is non-uniformity on the surface. So that could be a chemical non-uniformity. So on this surface here, we've got these coloured patches. These correspond to patches where we've got different contact angles, so different local contact angles. And so as the droplet spreads, it will spread at different rates on different parts, and it will lead to some hysteresis in its contact angle. Or it could be a physical roughness, like in this bottom case here, where this is actually from a real surface. This is from a Talisurf measurement of a real surface and imported into the code. And this spreads out, and you can see how the contact line pins on certain features to produce a hysteresis effect. But that would require very high resolution, and it limits what we can do then in terms of multiple droplets. So what we do instead is we just capture the effect of the hysteresis. What we do is we initially set our surface to have our wetting parameters such that the contact angle on the unwetted surface is equal to the advancing contact angle. And then once the surface becomes wetted, we change that so that it actually has a value corresponding to the receding contact angle. So if this droplet were then to start moving in a different way that led this bit to become uncovered, we would have a different contact angle experienced on that surface. So as this red fluid moves down the surface, this blue part here has its contact angle changed to the receding value. Okay, and this can be validated. So these are some tests that Khaled did against some previously published experiments of droplet impact, particularly looking at the droplet spreading diameter and the height of the droplet. And he found that a pretty good agreement actually in both the spread and the height. So here you can see the droplet oscillating as it impacts and then settles down, and under different conditions as well. We didn't have all the information from the paper on this case, so we could only really match the initial behaviour, but again it agrees pretty well with experiments. And we can also validate the footprint as well. So this is a different set of experiments where we show that the predicted footprint with our hysteresis model agrees with the experiments. And this just shows what would happen if we didn't include the hysteresis. We'd end up with a circular footprint here, whereas what we actually get is this elongated footprint. Right, and we can also capture this drawback effect. I'm going to skip over that. So I want to get on to what the main thing that Khaled was doing in his PhD. So he was looking at printing onto an idealized scratch. So here's a droplet, and we're going to base all our length scales scaled by the droplet in-flight diameter. It's going to impact centrally on a scratch, and so the dimensions of the scratch are given by W and D. D is the depth below the original surface, and it has these side ridges And these are added to mimic what happens if you imagine that a scratch was actually made on a surface. The material which is ploughed out of this groove here would be displaced onto the sides of the scratch. So it's an idealized representation of that material that's been displaced from the original surface. And that's why the volume of these matches the original sort of displaced volume here. And so what I'm going to show you is based on a particular set of parameters where we've got an advancing contact angle of 75 degrees and a receding contact angle of 1 degree. So we expect to see very little receding of the droplet once it's spread. Khaled also wrote his code for GPUs, for graphical processor units. That's a really good use of Lattice Boltzmann code. You can get a speed up of over 100 times by doing that. So that allowed him to explore a very wide parameter space. And this is what he found. So this has recently been published in the Journal of Fluid Mechanics. So this is his regime map, if you like. So what we've got here is the width of the scratch measured in terms of the droplet diameter. So here we've got a width which is the same as the droplet diameter, and then we've also got the depth going downwards here as well. So we've got shallow, narrow scratches at the top left and deep, wide scratches at the bottom right. Now you can see these different colours in here. These correspond to different behaviours which were observed. So I'm just going to illustrate some of those behaviours which were seen. So starting off in the top left, then. So in this situation, the scratch is shallow and narrow, so it's not really enough to disturb the behaviour of the droplet too much. So we call that a quasi-spherical cap. So if the scratch wasn't there, we would just end up with a spherical cap for our droplet shape. And this is pretty much a spherical cap. It just spreads nice and easily. It doesn't really recognise that the scratch is there, apart from these little bits here that go into the scratch. So down here, if we make the scratch deeper, we can actually end up with a capillary flow. So the droplet will spread initially over the surface, and then it will continue to spread. I don't know if you can see that still moving, that thing there. We could do with a better angle on this, really. The droplet actually continues to spread along the channel, so we call that capillary flow. So that's because of the capillary effect, it travels along the channel, and so that can lead to some elongated parts of the liquid. So this might be a problem for printing if you were printing two separate lines of a circuit parallel to each other. You could actually create a short circuit between them with this kind of connection. If we then make the scratch shallow again, but make it a bit wider, what happens then is that the droplet spreads both laterally and into the scratch as well, but the spreading now is not driven by the capillary flow, it's just driven by the inertia of the impact. So the droplet spreads a bit into the scratch, but then stops. It doesn't continue, but it has enough inertia to spill over the sides of the ridges and onto the original surface. So you get some kind of shape like this. You can just about make out the edges of the ridge there, that little feature. So we call that the inertial regime. And then you can imagine that if we choose a particular size of scratch, so if the ridges were wider, the droplet might not have enough inertia to spill over them. It might just reach the edge of the ridge, and if it does that, then it actually will pin on the edge through Gibbs phenomenon. And it will, so you end up with it pinned on the core, and it doesn't retract, and we end up with something called an edge pinned regime. And these lines here, these are theoretical predictions of this, which are based on previous models for spreading on flat uniform surfaces that Khaled adapted to account for liquid going into the scratch, and then looking at condition where the spread diameter matches the size of the ridges. So there's a whole load of previous models for spreading on flat surfaces, so uniform surfaces, and here's a collection of them. And the ones with asterisks were used in creating those lines. So those lines actually represent the mean and standard deviation of those models. And you can see they agree pretty well with the numerical predictions in terms of when that occurs. So have a look at Khaled's paper if you want to see more detail on that. If we have a shallow wide scratch, then we will have a semi-imbibed situation where the droplet doesn't spread enough to reach the outer edges of the ridges, it just sits on the top, and most of the fluid is inside the scratch. And then if we make the scratch deeper, then a lot of the liquid can go into the scratch. It still spreads onto the top ridges, but then it splits along the edges here. And again, we can make theoretical predictions of that by adapting those previous models to account for the fluid going into the scratch. Okay, so we started out talking about printed electronics and continuous printing. So this is what happens if you print a continuous sort of sequence of droplets over a scratch. Even though there's a scratch there and it looks like it initially breaks, the subsequent droplet sort of pushes a bit more liquid in and actually maintains a continuous line. Although you might have some resistance problems here because you've got a very thin layer of material. So that's in this regime. If we then change the depth of the scratch a bit, you actually end up with a situation where you can't recover that continuity. And you get a break in the printing. But scratches could perhaps be useful because if you actually print along the scratch, you can get a nice, sharp, continuous line like this. So they could be used in a positive way, I guess. That was Khaled's project, which concluded that Lattice Boltzmann was quite a good approach for this kind of problem. Surface defects can cause breaks in coalescence and continuity, and there's a lot more detail in the paper, so if you're interested, do have a look at that recently published paper. I spent a lot longer on that than I was planning to, but I do want to show you a bit of Tom's work as well. So Tom was also looking at inkjet related work, but this was motivated by reactive inkjet printing. Now the limitation of inkjet printing is that you have to be able to jet the liquids through a nozzle, and that can limit the type of material that you can produce. So the idea of reactive inkjet printing is that you can print 2 or more reagents which are jettable, which then react on the solid surface to create something else which wouldn't be jettable on its own. And there's all sorts of applications of this, but that's the motivation for that. So a key feature of this kind of printing is that the droplets have different material properties and they involve chemical reactions which require appropriate mixing. So what Tom was looking at was the mixing of droplets as they coalesce. So do printed droplets mix then? So this is from the same set of experiments that I showed previously in the talk. So in this particular case, we've got a sessile droplet here sitting on the surface, and another one with dye in lands directly on top of it. And in the middle of that video, it looks like there's actually some mixing because the dye seems to be blended. But then as the droplet recoils, you can see actually that second droplet is just sitting on top of the previous one. The sequence at the bottom shows that the droplets remain quite separate. Now the problem with visualizing inkjet scale droplets is that the droplets are so small it's very difficult to see inside. You can't get enough light in there to get a picture of what's going on inside. So typically what people do is study millimeter sized droplets where you can actually see inside what's going on. And what they do to make it relevant to inkjet printing is that they match the Reynolds number and the Weber number. Okay, so you adjust the fluid properties to account for the fact that you've got a much larger length scale and the speed as well to match your Reynolds number and your Weber number. So then you're dynamically similar to the inkjet regime. Now the problem is, when you're looking at mixing, is that we can't match the Peclet number at the same time. So the Peclet number is a measure of the rate of advective transport to the rate of diffusive transport. So it's defined like this. It looks rather like the Reynolds number, velocity scale, length scale, and then the diffusion coefficient is what D represents here. So diffusion is not properly represented when we have these larger scale droplets, and that's why here we don't really see any mixing. So we were wanting to study this a bit more and see what can happen. So because of this diffusion not being sufficiently rapid in the larger scale droplets, there's very little mixing that goes on. So really all that can happen is that the droplet flattens into a disk. You can get some diffusion over the disk, and then it recoils, and there's a little bit of blending in here, but it's very little. And the length scale at which you can sort of observe diffusion in a given time is given by this relationship. So if you've only got 5 milliseconds of this impact, you're only going to diffuse over 4 microns. And if it's a much smaller time, correspondingly smaller distance. So diffusion is not really having much effect. And really what you want to do in these situations is try to enhance the diffusion by stretching and folding. So that means stretching out this interface and then folding it back on itself to create striations, so many striations which can then diffusion can act over. But as we've just seen, there's very little scope for that in this geometry. However, there is scope for some jet formation, so we could have a scenario where a small dyed droplet impacts on a larger droplet and actually creates a vortex ring, and that can be driven by Laplace pressure differences, surface tension differences, and droplet sizes. So there are other mechanisms to be explored, and that's what Tom was doing. So I'll just show some of his experiments. So this is a situation where we have a sessile droplet and another droplet on top. So the second droplet was actually just gently placed on top, and then it coalesced. And you can see that here we've just got the same situation, no real mixing going on. But if we make the sessile droplet bigger relative to the other droplet, actually you can end up with a situation where you see a jet formed inside. And so this helps to mix things up inside to generate some mixing. And it's related to this formation of this bubble on top of the fluid. As this capillary wave sort of travels around the surface, you can see that bubble on the top there, which then plunges into the droplet and creates this jet. And Tom did some CFD simulations as well. So this was using open foam, so it's a more traditional kind of CFD, and got good agreement between when jets arise and when they don't. And it's all related to the formation of this bubble on the top here and how it gets sort of pulled into there. So the complex capillary dynamics on the interface produces this. So that was using open foam. There was a contact angle model in there as well. You can read about that in Tom's paper if you want to read more about that. And he also created a regime map. This one is in terms of the receding contact angle and the droplet volume ratio, and found conditions where you get no jet, or you get a jet, or you get some sort of transitional behavior in between. And he got good agreement between his CFD and the experiments. Now, in the literature, if you look at mixing of droplets, people tend to look at things just from the top view. And so you can see various examples where they claim that there's good mixing going on because it looks like things have all mixed up. And here, this is a case where we've got a droplet with a second droplet with pH indicator in it, and we've got an alkaline droplet in. So as the droplets mix, you get a change in colour, showing where they've mixed as the pH changes. But they give no information on the vertical dynamics. So what Tom did on a visit to Oxford was some experiments where he was looking both from the side and from the top on this situation where a droplet is impacting next to another one. And so we've got some videos to show of that. So we've got the sessile droplet on the right, the other droplet impacting on the left. And you can see here that looking from below, it looks like you get this lovely jet formed as the droplet impacts and spreads into the other droplet. However, when you look at this from the side, what you see is actually that jet is just confined to the surface of the droplet. Here it is, just at the top here. So from the bottom, it looks like, oh, we're getting some mixing going on there, but actually it's confined to the surface. And it's driven by this capillary wave again, which comes along here and sort of breaks just at the top and propels this jet into the original droplet. And then if we play about with the surface tension, so we make the two droplets different. So now we've got droplets here with different surface tensions. So in this case, the one on the left, which is impacting, has a lower surface tension than the one on the right. So the one on the right will want to pull liquid over its surface because it's got a high surface tension. It's going to want to cover that surface. It will pull liquid from the second droplet, and it will tend to spread things out more than in the equal property case. Whereas if you make the surface tensions opposite, so now the second droplet has a higher surface tension than the first one, you see that there's no jet formed at all, and that's because the surface tension here is pulling liquid from the original droplet into the second one, and it's inhibiting that jet formation. And Tom did various analysis on that. So this was the mechanism by which it happens. It's a capillary wave, which as the droplet spreads, it forms a ridge here, which then propels itself along the interface and up the second droplet, and then sort of breaks at this point to create this jet which goes into the original droplet. I'll skip over that. Tom hasn't published that bit yet. Okay, so just to conclude then, sorry I've taken quite a long time there, but the conclusion I can make from Tom's work is that there's a lot of rich behaviour going on there. So the free surface and wetting dynamics are important in actually influencing what goes on inside the droplet as well. So the surface jet formation hadn't been seen before, so that was a nice outcome that wasn't expected. Tom hasn't published this bit yet, but he's done some work on using a pH indicator as well to indicate mixing. So future directions are still plenty to do in here. So further validation of the numerical simulations, particularly looking at the diffusive effects, including heat transfer and chemical reactions. We didn't quite get onto that in Tom's project because we got lots of other interesting stuff to look at. And exploring the droplet length scales, and that's actually what Yetin is working on. So he's just started his PhD, and that's what he's going to be working on. Okay, so I'll stop there, and if anyone's got any questions, then please go ahead. Sorry, I've used the full time there. Thanks very much.